So the problem we're going to deal with is this sort of problem, which is a representative volume element that is subjected to a triaxial loading. And this means that you have loads in the x, the y, and the z direction acting at the same time on this domain, and want to see what behavior of the sample. And for this study, we're going to be using a voided aluminium material with different voids which are represented as these holes, and want to see what is the effect of this triaxial loading on this kind of system. This sort of study is really useful where you're looking at maybe the ductile behavior of the coalescence of voiding on a metallic system like this, and also maybe a hydrostatic effect or dilation effect on your system. So this is where you kind of do this triaxial loading effect on a system. Other cases where you may have to investigate something like this is where you're looking at something like a stress triaxiality effect quantification, or maybe something called a load parameter quantification, or even a shear stress ratio quantification. These are features associated with ductile loading, and we want to be able to see how you can actually do that. In the end, I will show you how to set up the loading, this triaxial loading, and also how we'll generate and discuss a little bit around the sort of result that we'll be generating from this system, where you see all the faces are being deformed continuously at the same time. So we'll look into that. And of course, finally, we're going to also look at stress strain data, the triaxial plot, the actual stress strain data from this kind of simulation. So that's what we're going to be doing in this video. So let's sit back and relax as we get started with this modeling. Now, the first thing we need to consider here is actually the virtual domain. So, like I said previously, the virtual domain here is going to be a voided aluminium material that is shown in this case. And the dimensions of this aluminium are 8 by 8 by 8 millimeters. It could be any dimension. And the void configuration that we're using within this case is going to be made of sphere with different diameters. And this is just because I wanted to have something that is polydispersed distribution of the spheres. And so different diameters were considered, and the diameters under consideration here are 3 types of diameters: a small diameter of 1 millimeter, a middle diameter of 2 millimeter, and a large diameter of 3 millimeter. And of course, there is also a volume fraction associated with the distribution of the phase. In this case, I'm looking at a cumulative void volume fraction of 15% for this case. The voids have been distributed randomly, because it's really important to make the voids random in their distribution, because that's how voids form in reality. Some other people can study and order the arrangement of voids, but I wanted to treat something that is quite realistic and representative. And so in this case, a Monte Carlo method was used to generate this voiding in a random sense, so that it reflects what reality would be. Now, of course, the question you would ask is, how on earth did they actually create that? And this comes back to a software that I wrote, which is called Monte Carlo 3D. It's for creating 3D representative systems. In this case, a void, it can also create other kind of systems. It's actually a software that I've written. What it does in the end, apart from dealing with the Monte Carlo method, is that it generates a Python script that the user can then harvest and then use it within ABAQUS to run the simulation. So this is just a snippet of that Python code. And then with that Python code, you run it through ABAQUS, and ultimately you can generate the system that we're having here. If we don't do it this way and want to do it by hand, it can be really quite challenging to do. So you do need maybe a script like this to help you with doing that. If you don't want to do this and you want to do it by hand, again, the video that is here will help you to do it physically, but in that case, that would be for particular composite. But in principle, I do encourage you to get hold of the software. If you really want to get hold of this software, look in the description section of this video at the link that will direct you on how to get hold of the software. Now, the kind of loading that we're going to use in this system would be, this is the domain, so it's going to be a triaxial loading. So in effect, we're having load on all 3 dimensions as shown in this system. So we've got a loading in the x direction, and these are displacement loads. So I'm going to apply displacement load on the system at just the corner nodes, those 3 corner nodes, one on the x phase, the other one on the y phase, and the other one on the z phase, to reflect this triaxiality. And the interesting thing about that is that if I'm applying load on the x direction, I need to then hold the back direction so that I have a pure uniaxial deformation. And the back end here is only going to be fixed in the one direction, so it's then free to contract in the y-axis. Now, with respect to the y-axis, if I'm going to pull in the y direction, then I need to also hold the base here, which means I'm fixing it in the y direction of the 2 axes. so that again it's able to contract in z-axis and the x-axis in this instance. So what I've identified here as the base face here is the y base face. For the x-axis, I'll call it the x-back. We're going to deal with that when we go into ABAQUS to demonstrate how this is actually done. And then with the z-axis here, if you're pulling in the z-axis, then you need to constrain it on the pure z-axis only, which will be the 3-axis. And then I've identified the back face there to be the z-back face. And so when you combine all these three kind of loading, this is how exactly you're going to prescribe triaxial loading on a system. In this triaxiality, you have only 3 uniaxial load acting on the system. But then the interesting thing with this is that how on earth do we translate a load that is applied onto one single node at these 3 corners to actually deform those faces? And then this brings in the idea of a kinematic coupling. So essentially what you will need to do here is that if I'm applying the load on that corner node that is there, then I need to apply a coupling between this corner node and the whole face is the x face here, which I call the x front. So that with that kinematic coupling, as this point is being pulled, that face is also being pulled along with it. I choose to do this because then I want to manage the way that I extract my stress and strain data from my system. I wanted to extract forces that I'm going to then divide with an area to create my stress and strain data. And this is really important for a system like this because you have a lot of elements in the system, and so if you are tracking it by element consideration alone, there will be a lot of variables in the system and you'll probably run out of memory and it will be difficult to do. So this is the way that I'm going to do it, so that in the end I'm going to be tracking only the reaction forces and displacement of the corner node. We'll speak about that in a moment. Now the same thing applies with the z-axis. So again, if I'm tracking what's happening in the z direction, connecting this node, and then I have to fix it with the whole face here, which I call my z front face. And the same thing will apply with the y-axis. The top face here is called the y top. So we'll demonstrate that again in ABAQUS. Now the next thing is that after we've done that, because I'm tracking, I'm applying my load and everything on those individual corner nodes, I'm going to ask ABAQUS to output for me the displacement of that point and the reaction force on that point in the one direction, which is the x-axis in this case. For the y direction, I'm going to ask for displacement in the y as well as the reaction force in the y. And then for the z-axis, I'll ask for the displacement and the forces in that direction. With that information, for example, for the x-axis case, then I can then define my stress in the x direction to be the reaction force divided by the area, the initial area of that face, and the strain will be the displacement in the one direction divided by the length of the material, which is the edge length in this case. So this is a normal. Now if you look a little bit more, one thing becomes interesting because my surfaces here are actually irregular. Okay, so the area here, which I call AXX for the stress in the x direction, will actually be this region, and it's irregular, so it's going to be a little bit difficult to find. And so we will be using a Python script that again will be available in the description section of this video, which to probe that area and extract what exactly that surface area would be, because due to the presence of these voids, it's difficult to calculate it accurately, just by arithmetic. You then need to actually use Python to probe that system and extract that. So I'll be telling you how to do that in the course of this video. So that's really the background to what we're trying to do. So now let's go into ABAQUS and begin with creating the virtual domain. If this is the kind of content that you like, please, I do encourage you to subscribe to this YouTube channel so that when contents like this are made, you'll be the first to see it. I also want to highlight that there is a CM Videos Insider group which I regularly send every week newsletters talking about behind the scenes in CM Videos and more about products that are available on the CM Videos website. I also publish in this newsletter reflections from my perspective on a lot of computational modeling issues. If you're interested in this kind of thing, please do subscribe to the newsletter. You'll also be able to read up to 100 articles already published on that newsletter. Thank you. So like we said, the first thing we're going to do is to create the virtual domain that we're going to use for this solution, for this modeling. And this is sort of how the virtual domain is going to be created. And we said that we're going to use a Monte Carlo gen to create that. A Monte Carlo gen would output a Python script. So let's look at what the Python script would look like. So this is sort of the output of Python script, how it will look like. So right at the top end, we get a little bit of information as to what this specific script is going to be like. So it's actually been created for ABAQUS using MonteCarlo. And MonteCarlo actually wrote the script for us to use. So it has the normal information of importing all the relevant ABAQUS object libraries that you need. And then it opens the ABAQUS model. It starts working your way through creating the metrics part and then creating the voids for all the parts that make up the system. So, and it actually creates individual each part depending on how many number of parts that are required. So that's the information. So we're not going to look through the script at all. So all I'm going to do is I'm going to say Control A to select or Control C to copy. And then I'm going to go to my ABAQUS. So here in ABAQUS, we want to bring in that Python script into our ABAQUS. And because I've already copied it, so I'm going to get to the kernel command at the foot of this ABAQUS system. So if I expand it and just paste it there. So what it will then do is that it will run through and you can see exactly what the code is trying to do. So essentially it's creating each of these individual voids one by one. And because the idea here is because we have different diameters of these voids and you want to create them specifically uniquely in the way it would be. And this is really the way MonteCarlo tries to incorporate this principle, because you may want to have different diameters or the same diameter, and so it is uniquely deals with its void exactly as it is supposed to be, and that's essentially what is going through here. So now it's creating the metrics and also assembling all the voids together, so you could see how it's them distributing them in their positions exactly where they need to appear randomly using this Monte Carlo methods. And once it's finished doing that, so it deletes the original models that it created, because then it has created the instances of those materials, and that's essentially what you're seeing here. So it's deleting them, and then I asked it to trim off the boundaries so that it can actually review exactly what is required, what we're dealing with, and that's what is done here. So it created it initially within a domain, and then because I asked it to trim off the edges, this is just a feature that was incorporated in MonteCarlo. You may not want to do that, but this is essentially what I asked it to do. So it trimmed off the edges to the dimension that I want, revealing all the edge voids, and we now have the model that we want to work with. So we now have the output. Say there's a representative volume element with 10 cubic. So originally it was 10 by 10, but because I've asked it to trim it down, it trimmed it down to 8 by 8. And this is the number 1 version of it, and there are 61 spherical void in the system. And so I'm probably going to rename it, so I could just call it, voided case 1. And so if we then open what we have, so this is the full model exactly as it's created, but I can also look at the voids only. So this was the initial void that was created, and these voids were then used to extrude cuts, and then we get the voided system here. Also, there's a bit of materials, because within the system, in writing the code, I asked it to supply the materials. So for example, here we've got the matrix, which is basically made of aluminium. And the particles could be, in this case, void, so it's not important. If you're trying to do a different problem, then maybe you actually have the properties of the particles. So what we have here is basically the Young's modulus and the Poisson ratio of aluminium. So what I'm going to do, because I've already ran the simulation before in this number case, I'm going to import the actual matrix model that I used. So I'm going to copy. So if you go to the top here, it's a model copy object. So I'm going to copy from the one that I know that I've done before to this case, and all I'm looking to copy is the matrix phase, and probably I could look at maybe a section, the matrix section, and then click OK. So obviously it's found that it already exists. I say yes to all, and this is fine. So now if we go back to the system and look at what we have under the material, the actual properties of the matrix will now have plasticity in it. And so instead of supplying it by ourselves, then I'm just using what I've already used before. And so this is fine. So we've got the properties. We've also got everything here. So we then go back to the full model. The section assignment has already been done as a consequence of the matrix file that was written. So we're not going to worry about that. Then you could try and mesh it. So if we try and mesh, so I'll use what it's recommending as 0.4. And I could then ask it to use tetrahedron. Tetrahedrons are usually better because they will always mesh a system that is quite heterogeneous and complex in architecture this way. Then we can go ahead and merge the model. So the model looks okay, but I'm going to turn off the mesh at the moment as I keep working along. Now the next thing that we're going to do, which is really important here, is that we need to create the sets, the faces we are going to apply our loads on. So under this region, I can say, okay, the first set I want to create here is the X front. So the X front, so I'll just hover around here and select the front face. So that's my X front. Now if I go back again and say, okay, Y top. So we want, because we're going to use it to apply our loading later on, and then I'll do the same against Z front. So, and that will be this face. So if I just go to the set, so you can find, okay, we've got different set associated with the system. So if I turn this to the back, there's clearly no set associated with the back, and we know that the back is the X back. So I'm going to call this my X back, so the set associated with the back, and then I'll select that region so it identifies that it's a different system. And so now if we go back to this end, so if this is the Z axis, so this will be the Z back. So again, we'll do the same thing. So this will be the Z back, and then we'll continue, and then I'll highlight there. Okay, so that also is fine. So nearly all the sets are located except the Y base. So I'll go back and then say, okay, my Y base, double click on set, Y base, and then I'll select the base here and then click done. So this way, we now have all the sets that we're going to use for setting up the system clearly identified. But because we're going to be assigning our loads on the corner node, so it makes sense to identify them as reference points. So if I switch this to assembly module, and then I'll go to tools at the top, reference point. So the first point is right here, so I'll associate that with that one. And then I also look at this end and I associate that with this one. And then at this other corner, I'll click on that. So we've got three of them, and I want them to make sense. I want them to mean something. So I'm just going to go and rename them. So if I rename this, so I'm going to call this my Y reference point, something like that. And then the two case will be the X reference point. So this will be X point, our point. And then the Z one, I'll rename them and I'll call it my Z point. Remember, we're doing this within the assembly module. If you try to do this in the part module, it will not work because only one reference point is associated with one part within the part module. But when you get to the assembly module, because you're combining multiple systems, it will allow you to apply different things. So we basically have all these different reference points identified, and we can then use them to make our connections. So now we've got all the reference points. We then need to actually label them as nodal set for them. So I'm going to call this YRP set, and then we'll attach it to that point. So now we've labeled it. So then go and say, okay, X reference point set. So we'll attach it to that particular one, and then we'll also do our Z reference point set, and we attach it to this one, because this is the only way we can actually call it within the simulation. Yes, we name them as reference point, but we need to create sets for them because that's how we're going to use it later on. We will probably need to create a step. So I'm going to do a simple static loading. So I'll have a loading step associated with this, a static general loading. So again, you can do whatever type of analysis you want to do. So once we've got that, then the next thing is to create history output for them for all 3 points. So I'm going to call so let's just call it YHO, which is Y history output. And this Y history output will be associated with the set that we've created, which is the Y set. And in the Y direction, we're only interested in reaction force in the 2 direction and the displacement in the 2 direction, as shown even in this picture. So we do the same thing for the X reference, X history output. So with the X history output, again, we're tracking only the X reference point, and we're looking at reaction force 1 and U1 as also shown here. And then finally, we get the Z history output. So we'll do the same. All we're tracking is the history output of the Z reference point, and we're looking at reaction force in the third axis and displacement in the third axis. The other thing that we need to do as still part of this is to think about what constraints. We need to constrain those reference points as shown in this figure so that it understands that when you're moving a reference point, the phase has to go along with it. So we'll use this constraint of, so let's call it Y equation. It will be associated with a kinematic constraint equation, a star equation as called in ABAQUS. And so what we are looking for here would be 1 here, and the set we are working with for the Y-axis, for example, would be the Y top, because it's the top that we want to apply our load to, in the 2-degree direction, and we're linking it to the reference point at the Y, and minus 1. So what this basically is saying is that whatever is happening in this is equal to what's happening at that point. So it's a canonical equation. Again, if you're interested in learning around this, I've already made a video on how this works for a porous media, which you can see in this video. Okay, so this is the Y equation. So we need to do the same for the X equation. So X equation, so we'll do the same. And basically we have 1 minus 1. And then at this point we have the X not back, X front, because we are working with the front axis here, and the X reference point is 1, and we're interested only in the one direction, which is the X axis. So finally we have the Z equation, and with the Z equation, again 1 minus 1, we're looking for the Z front because we're applying our load on the front, so which is this point, and we're linking it to the Z reference point in the 3 axis. Okay, so this way we have connected what's happening at that node to those faces, at this node to that face, and that node to that face. So the final thing to do is just to apply the required boundary condition and load. So let's apply boundary condition. So I'm going to say my Z back, okay, let's say Y base, okay, roller. So we want to apply a roller load. It will be an initial boundary condition with displacement. So what is the base? So we're working with the Y base, so I'm going to select the Y base here, and we want to only constrain it in the 2 direction. So what that means that I'm now constraining only in the 2 direction as I apply load in the top to pull it. So we'll do the same with the X. So I'll go to say X back roller, still an initial boundary condition, and we are attaching it to the X back, and we are constraining it in 1 direction. And you can see constraint there, and then you move at the front. So finally we'll deal with the Z back roller. So these are roller supports. So, and we're working with the Z back, which if we highlight, it shows as the Z back, and we are constraining in the 3rd axis. So this way we've provided a boundary condition that constrains these systems in the right directions. Now we then need to apply our load. So I'm going to still use the displacement boundary condition as shown here to apply our load. So I'm going to call it my X tension, for example. It would be a loading step as against an initial step. So with the X case, we go to X reference point, and with the X reference point is the X axis that we're dealing with. The system is of length 8 millimeters. So if I do 10% of that is 0.8, so we can apply a 0.8 displacement. So you see now we're applying this load at this point. Is constrained at the back, so you have a pure uniaxial deformation. So the same thing would I have to apply with the Y tension. So if we want to apply a Y tension as required for this, so I'm going to apply it on the reference point, and it will be in the Y-axis. It's the same 0.8. So it's a triaxial loading and applying the same load in all directions. But as part of a parametric study, you may want to vary the sizes of the load in the X, Y, and Z direction. And all you need to do, so let's say for the Z case here, so let's say a Z tension. So I'm going to apply it on the Z reference point, like we stated before. So only in the 3rd axis. So I could put a different number, maybe 1.2, so that I'm not necessarily applying the same the same quantity of load. But for this demonstration case in this video, I want to keep them as all 0.8, so that we have equal loading on all faces. And then we're going to study our result and see what is happening. But as part of a parametric study, it may be essential that you vary the sizes of load in this triaxial loading type and see how that will affect your result. So basically we've got the 3 loading, everything is set up properly, and we can then finally create the job and run. I've already run this, and let's just look at the result that we obtained. Okay, so when we ran this is the sort of result we obtained. If we just animate it a bit, so you can see what it's basically showing us, some really interesting results. So this face is deforming, that face is deforming, and the top face is deforming. So essentially, and this is why you're looking at this coalescence of voiding. So if you go voids as they expand, then these voids are being forced to coalesce, and then you are assessing the effect of coalescing of these voids due to this triaxial loading. And if there is a void collapse or a dilation effect, you could also study the effect of that, because every point in the system is seeing this triaxial stress state. So if you're looking at hydrostatic effect of a system, again, each system is experiencing this triaxial effect. And hydrostatic effect, like you know, is essentially assessing the effect of pressure around your system. So it's a really wonderful set of experiments that you can do numerically, and this way that I've shown here is a beautiful way that you could actually do that. And so the result is sort of what we will expect. I mean, just something else that I would probably like to look at is the displacement, just to give you an idea. So again, this system is the system that is seeing the most deformation, and you could see it almost appearing independent by itself. So some other thing that is also essential to look at is the plastic strain, because we allow plasticity to build up in the system, so we can assess how plasticity is building up. It may also be important for you to open up the system and assess. So you basically open the system and try and sweep through to see what's happening. So let's just go to the end of the time step, so you can see where the plasticity is building up. And this is really around the voidings, because the voids are expanding, and if you see around here, there is a coalescence of these voids which probably were not there initially at the beginning. So these are some of the interesting things that you want to study as a result of this. So let's go back to the stress. So as a result of what you're trying to do, and using this triaxial loading approach is a beautiful way for the student to actually investigate this. So that's visually what you can see. But what also will be interesting, can you also look at the stress strain data that is associated with a system like this? And so this is what I'm going to show. So let's look at how do you actually get the stress strain data. Also, when we're setting up the result, we ask for a certain history output. So if we go here and under there and track the history output that we asked for, it was quite a few set of history output, and this is why I like to do it this way. So you've got the 3 reaction forces. I'm going to press down shift, select the 3 reaction forces associated with the different stresses, and then I'll select these 3 displacement associated with them, and then I'll just plot them. So instantly when you plot them, it gives you a trace, a measure. Sort of the forces are these ones as a function of time, and the displacement is the same in all directions. If the loadings were different in all directions, then the displacement would be different. But because we're applying the same load, so I'm not surprised that the displacement is the same in all directions. So that's the visual view, but I want to do some operation on this data. So let's go to plugin, tools, Excel utility. All I want here is the current plot, so I'll press OK. So it will export it into Excel, and then we basically have our result like this. Our first data here is reaction force 1, reaction force 2, reaction force 3, and then the next one is the displacement in 1, displacement in 2, and displacement in 3. So what I will do is that I'll leave the first is always time, then the value. So I'm going to select, press down shift control, select all these time values and just delete them, because there's no need repeating them. And then in the end, all we have is the time and the reaction force 1, 2, reaction force 3, U1, U2, and U3. So I'm going to copy that and do some formatting with that. I've already formatted a template that you're going to use, which is in the description section of this video. Please do find it if you're interested. So this is sort of what the template look like. So I'm just going to paste the data we obtained in that window. So if we paste it, then so our time, the reaction forces that we talked about, and then it will try to then calculate these values. Admittedly, so the length I already know, I'll put that in. Now there is this really interesting issue here, which is around the area. What is the area associated with the system that we're dealing with? On the X phase, the Y phase, and the Z phase. I've also again done this and I found these numbers, but let's just demonstrate it for the X axis, for example. So I talked about a Python script that I wrote. Again, for doing this, please, it will be available in the description section of this video. Let's work with that. It's something I wrote a while ago. So basically, the model name, what it asks you to tell it the model name that you're working with. So the model we're working with is this. So I right click and click OK, and rename. So I'll just Control C to copy this and then replace that as the Python script that we're working with. Now, what is the part name? So this is the part name that we're working, full void model. So I've already done that, full void model. Then it asks you a face reference point. I want you to give me a face reference point for the face of interest that you want to extract the area of. So in this case, if it is the x-axis that I'm trying to do, so let me just activate the show the meshes, because when you show the meshes, you can have multiple points from the mesh that you can track. So this is the face where I want to, so any point here I want to find what the area would be there. So again, we use the same system as this. Rather, now I'm wanting the point or the node, so you can then select any point on the node there and click done. So you can see it now gives you what number it is. So it's 9 on the x-axis, 5.8. So I'll just copy that data, Control C, then go back to my Python script, so which is this, and paste it in there. So it tells me 9 on the x-axis, 5.09 on the y-axis. So that's the point that belongs to that face of interest. Every other thing will remain, so I don't want you to worry about that. The key thing you need to remember is that you can print the volume of the system and also the surface area, which is really what we want. So I'm going to do Control A to select all, Control C to copy, and then I'll go back to my ABAQUS for it to actually run with that script. So I'm going to run it under the kernel command. So again, we go to the end of the kernel command. So if I paste it there, then it will run through, and you can see it's printed the area for me for that face. It printed the area, so I can copy that area and go back to my Python script, to my Excel file, and paste it. So I did the same for the y-axis, so the same thing for the z-axis, and we also get a number. So once you found all those numbers, what is your strain? Remember, our calculation shows that your strain will have to be something in the x. So the displacement in the x, so if you look at what's happening here, so we're looking at displacement in one direction divided by the length parallel to that direction, okay? And that's what we found. And then what would be the stress? The stress would be, okay, the force in that direction divided by the area in that direction. What I've done is I've added a really minuscule value of, because I just want, later on we'll talk about, you know, triaxiality effect and all that. So I just added 0.001, but it's not important. But this is just a numerical fix, just to prevent having a 0 divided by 0, which is undefined. This is why it gives us a really small number that is insignificant, but it's okay. And then we'll do the same thing for the y-axis. The y-axis will be the displacement in 2 divided by the length, and then the same thing. So we find all that and we find our data. So the other thing I was interested, because this is really useful for looking at triaxiality effects and load parameter assessment. So what could you do? So I decided, okay, one of the parameters you're looking for is what is called ρ11, which is the ratio of the stress in the one axis divided by the stress in the two axis. And so that means what we need to then do is the stress in the one axis divided by the stress in the two axis. So if this was originally 0, 0, we're going to have 0 divided by 0, which is indeterminate and doesn't make sense. So we don't want to have that. So what I'm going to then do is to sort of slightly introduce a very small measurable number, which is 0.0001, and divide by 0.0001, something like that. And in the end, we're starting off with a value of 1 as a stress ratio for at least this problem that we're dealing with. It doesn't really matter that much, but this is just a numerical thing that I did in order to allow you to get some meaningful result. And then you apply it for all of them. The key thing is that they are coming up just around 1, which is sort of what the theory says. So the rho 33 divided by S2, 33 and S2. Again, this is depending on the combination of your stress. So this is why it's important as this triaxiality assessment to have all that. So the 3 direction will be 33 divided by 322, which is the stress in the 22. So you find all those numbers. So this is sort of a stress triaxiality result that you get for this system, showing what's happening, the stresses for the stress in 1, 2, and 3 axes, which are all of them acting at the same time. And this is really interesting because when you think about what's happening here, why are they all different? After all, it's the same load that is applied. But the clue already you can see from above. The first thing here is that the areas of the surfaces are actually different because of the effect of the voids. And so that suggests that it would then have a different stress history because the areas are the same. And also because internally within the system, the distribution of the voids in some cases may be intense, and therefore in some cases it may not be. And so you tend to have different stress forces and reactions to the system, and that's what we see here. Now, I went on to plot those stress ratios, the row 1 and row 1 and row 3 data, and then you can see they are all sort of hovering around 1. And for a different combination, you will also have different values like that. But this is just an extra thing that I did just for people that are working with, stress coalescence and their triaxiality assessment. And this is sort of what you would do. So obviously with this data, you can then go on to calculate the stress triaxiality ratio, the load parameter, the shear ratios, and other essential things. So that's all I wanted to show in this video. If you are interested in just understanding how porous media can work in terms of extracting stress strain data uniquely, like I mentioned earlier on, again, this is a video that will help you. Thank you for your interest in this video, and I'll see you in the next. Bye-bye.